So it's our pleasure today to have Markus Hecher here, who will tell us about answer set programming. So without further ado, we're happy to have you here, please. The floor is all yours.
Thank you very much for the introduction. I guess this is why the academic forum was better. A bit of a setup time. So this is joint work with actually a bunch of people at Vienna, but let's see how far we go. So start with a brief introduction. So in the last couple of decades, you know, from set solving and many other areas, we have seen that there is a significant progress in how we deal with the really hard problems, right? Instead of set solving, there is also another paradigm, which is called answer set programming. And this paradigm is quite flexible and it allows you to model problems in a generic way. So it's a really general problem modeling and solving framework where the problem we want to solve is modeled by means of a logic program. And the solutions to such a program are called answer sets. It is not only of interest to academia, there are also industrial spin-offs. And the problems we're solving there are, for instance, of industrial nature or, again, industrial nature, like problems that are interesting to Siemens. There are also nice applications in the logistics domain. This is a classical warehouse scenario where we want to transport or we want to move shelves to certain locations by robots, and the robots should not collide by doing so. It is actively used for train scheduling. It's used for the Swiss railway company, SBB, to compute optimization problems. So come up with like good train schedules incredibly fast. And quite recently, it has been extended for the computational biology domain. So this is a paper at III from February, actually. And this guy here, Polly Loic, I talked to him quite for a long time, and he kind of convinced me that in their domain, in this computational biology domain, so far they couldn't manage to apply SAS. For some reason, this logic-based formalization or this rule-based formalization that ASP offers shows a very nice performance. And they tried really hard. They also tried with other SAT experts to gain the same performance that the ASP has. But for some reason in this domain, ASP seems to work extremely well. So for the computational biology and these rule-based formalizations, seems to be the thing to go.
Markus, do you want to check your video again? We lost your video for a while.
Yeah, I think it's not doing well, I guess. Thank you very much. Okay, so these examples have in common that all of these are essentially combinatorial problems, most of them optimization problems. And to kind of briefly show an example, a very simple one. Let's just say we want to express reachability. So we want to reach from our source a certain destination. So the question is, how can we reach our goal? And with ASP, this is fairly simple to express. We just need to show and to state that the source is already reached, right? So this is a fact, we reach our source. Whenever we have something is reached that is not yet our destination, then we pick exactly one outgoing edge, right? This is what we want to have. We want to have a path. So we pick, for instance, this edge. And the second important rule that we need to express is whenever we pick an edge, we reach its endpoint, right? So this one here. And these two rules are almost enough in combination with the reach of the source. Just one tiny thing still missing. We need to state that unless we reach the destination, we do not have a solution. So if we do not reach the destination, there's no solution. And this is all. This is all what's needed for reachability. Now, you might not be that impressed because reachability is an easy problem, right? But in optimization, we usually have way worse optimization criteria on top. We could have negative weights like benefits. If we use this edge, we get whatever, some sort of reward. Maybe there are combinations of edges. If we use these two, we get some sort of discount on this edge. Whatever, it might be really complicated. optimization criteria on top. And ASP also offers something for this. We could say we want to minimize the costs of all the peak dashes, some of the costs. So
is it important for us to understand the syntax in one
No.
or two, or we should just go with the flow?
we just go with the flow. I'm almost done. I would now start from scratch with how this formalism works. This was essentially the reason why I want to go to the Blackboard, because there are so many. So thanks very much for the comment. There are so many syntactical elements here. You could also make it without it, but then this essentially boils down to two rules. So this is really one of the simplest way to write it down. Nevertheless, we will start from scratch in a second. So maybe to give a brief summary before we go into the details. Logic programming is this sort of declarative modeling problem-solving framework. It is the union of different areas of research. So there is a bit of large representation reasoning in there, a bit of database theory, logic. So it's really the combination of these. And they're very efficient tools available. Applications I already talked about. On top of that, what ASP offers is this kind of first order like flavor, where we can express, and you have seen this first order like flavor, right? I mean, these are variables on the first order level. Whenever I reach something, then this has to be done, right? So we have these first order variables. So essentially solving is, or evaluating an ASP program is comprised of two phases. One is grounding and the other one is solving. So with grounding, we just instantiate all these first order variables with elements from our domain. And by solving, we essentially evaluate the resulting ground program and ask, is there a solution? We'll mostly focus on solving here, but we'll also maybe briefly touch grounding. So I guess this is it for now on the slide part. Let's just go, the video is still fine, right?
Video is fine.
Perfect. Let's just go to a more interactive, like, I'm very grateful for this comment, and I heard these comments a lot. Like, there are so many different syntactical elements. Why is this related to set? Like, this feels so much separated from set. And I want to show that this is essentially just from the conceptual point of view, a mild addition on top of set, on top of Boolean satisfiability. Is there anybody who is not familiar with set? May they speak now or be forever silent? So I can assume that Boolean satisfiability is not perfect.
You probably want to unshare your screen note so that we get like the
Thanks.
wording flow.
Right. I mean, you put those perfect. So what is a logic program all about? We have rules, and rules are of this form. We have these are all essentially in the ground setting.
Sorry for nagging you again, but I think we need a larger font. Just
Even larger?
Yeah. Sorry, but
No worries. I'm flexible. Let's see, like that.
that's fantastic.
Perfect. So these are essentially variables. Just consider them to be like Boolean variables. For now, this is fine. We have negation as well. So what do we see here? Whenever all of these B1s and so on until Bk are derived, and none of these negated B's are derived, then we need to derive A. So it's something very constructive. Conceptually, it's like a logical implication. But in addition, we have this constructivity on top. So how does this look like? Semantic-wise, the semantics are as follows. We take a set of the variables. Of what? Well, we don't just have one rule. Usually we have a set of rules, similar to a logical formula, right? It's a conjunction of clauses or something. Here we have a set of rules. Usually these are called programs. Well, let's just abbreviate it with P. So a set of atoms of, or a set of variables of the program. here's an answer set, so a solution essentially, because it's a set that answers our question or problem of the program. If first M satisfies the program in the classical usual meaning of Boolean satisfiability. So this is essentially just set plus on top, we require justification for everything we derive. And this comes a bit from the kind of constructive math group or from the constructive math branch, where we want to say we cannot derive information unless we have a justification or a reason for it. So in addition, we require a justification, which means for everything we derive, so for every variable in the set M, we have a rule in the program that proves our variable. Well, let's call it justified. So what do we mean by this? We have satisfiability plus this justification property on top. What does it mean for an atom to be justified? Any questions so far? What do we need to define? What's still missing?
So P is a set of rules.
Yep.
And the rules are at the
Yep.
top of, and the consequence of the rule to the left can be anywhere literal, negated, unnegated, or
No.
it is unnegated.
No, exactly this one.
Okay, so
But
it's something positive.
Yeah, but I leave myself the freedom to just shift around here. This is really just like this part is like a conjunction, the body here, and this is just a single variable. What I didn't define so far is, I mean, that the model satisfies a program. It's just Boolean satisfiability. So everything that's in M is true. Things that are not in M are false, right? This should be fairly clear. What I didn't define so far is justifies. What does it mean for a rule justifying an atom or a variable? Usually in ASP we call these variables atoms, but it's essentially the same. What we mean is there is a rule with A in the head whose body is satisfied with respect to this M. So in the sense, we found a rule that gives us justification for M, or that actually derives justification for R, or that actually derives our variable, kind of. What do we mean by that? Let's just do a brief example before we give more formal details. Let's just say we have a program of this form. This is a classic. Okay, I shouldn't write it at the top, right?
No, that's fine. That's fine.
It's fine.
Just keep the font size large.
Okay. Thanks for monitoring the visibility. In this example program, for instance, what do we have? We say, unless we derive A prime, we need to derive A. Unless we derive A, we need to derive A prime. So we have this kind of cycle between both. What are the suggestions for what should be the result here? Like, what are the solutions of these? Or how many are there? Let's just count them. Exactly, it's two. One is A, and the other one is A prime. Why? Because the one thing needs the justification of the other, so it's only justified. A is only justified if A prime is not derived. A prime is only justified if A is not derived, right? So there are two solutions, and this is exactly what we get. So with this, we kind of model a guess, similar in satisfiability, except in satisfiability, the guess comes for free, right? We can just decide, set it to true or to false. But this kind of simulates our choice. so to say. And now on top, we can make rules, right? We can add constraints. For instance, if we would want to show that this is the same power as set, but it's at least as hard as set, we have a guess for each variable, and then for each clause, we just invert the clause and have it as a constraint. So the constraint would be something like, let's just do it as an example. So if our clause would be like x or not y or z, the constraint would be if we have not x or y, sorry, if we have not x and y and not z, well, then we don't have a solution, right? So if the body is satisfied, derive nothing, and this is not what we allow. I mean, there are some dialects that actually put a bottom here, but usually an empty head. I like this notation better because it's will be more clean. The semantics I have in mind is more compact, but you can consider there's a bottom here. So if you, this is essentially a kind of a no good, right? This is no good. This is a clause and this is the no good. So this is essentially the MP hardness proof for set, showing that this is already, now we don't even have semantics, right? Let's just go back to semantics. What does it mean for a rule to justify a variable? What we have to, so this is the rule. Let's just a brief definition. So we say R justifies A if, I think here the if is missing as well, or this definition, whatever. R justifies A if essentially R is of this form. And now I'm doing a bit of like a syntactical clash just because I'm a bit lazy in writing. I group all my positive variables and all my negative variables, those are not literals, in this form. So the head is A. The positive variables in the rule are BR plus, and the negative variables in the rule are BR minus. I mean, we can kind of show this here, and I don't know, maybe make an asterisk just to remember these are not the literals. So, but I don't want to write my head off. It's really just like a small abbreviation. So the rule is of this form. And what else do we need? This has to be true, right? So what do we mean? BR plus is contained in M. What M is not here. Yeah, we also require M with respect to M. Positive one is contained in this, and none of the negative ones are contained in there, right? Because otherwise it would not be proven. So if we intersect it with M, it should be empty, right? This is kind of the immediate provability thing. But now we do have a problem, right? What sort of problem do we have? What would you say if we have a program? All right, just this. Our program looks like this. We have, if we derive A, we get B. If we get B, you get C, and then we close the cycle. What is the solution? What should be the solution of this program? So we get kind of this.
Oh, empty would be a solution.
Yep. Exactly. So the only solution is the empty set.
Isn't everything a solution as well?
No, why? That's exactly the point. It would be a solution in kind of set, but here you kind of cheated your way into it, right? You said we prove A by having A proved, kind of, right? You prove A on the assumption that you prove A. It's not a proof by A, right? From the constructive kind of sense, in the math kind of sense, right? You can just say you showed an open conjecture because you showed an open conjecture. Well, It's kind of this, but that's exactly the point. And it's a very good question. It's subject to the
But the
definition.
definition
Exactly.
now seems to
Exactly.
allow the
Yep.
simplicity, right? So
Exactly. So we need something on top. That's exactly the point. And I'm very grateful for both of your comments, to be honest, because now this is exactly the learning effect we want to have. We need something on top. What do we need? What would you do here? And this is why I like this definition the most. It doesn't cover extensions, by the way. There's another definition we can go into. But this, for me, is like the most natural definition of ASP, I would say. How should we define it?
Did you say that M minus R justifies all the BR guys?
Sorry?
Would it work to just say that M minus the rule R justifies everything in BR plus? Will that take care of our problem, or do you need more than this?
No, you need more than that. Because there could be negations here as well, right? It could be a really large cycle. If you want, we can also add something like this here. So this is not responsible for proving something, right? So what we need really is we need to order, we need to care about the order of derivation. So what we want is essentially, maybe we start with A, then from A we prove B, then from B we prove C. So what we could add is, for instance, A as a fact, right? Because if we add A as a fact, we get this one here, and we get the justification for the whole cycle, right? Because the cycle is justified, but not by itself. It requires an input from outside, right? It requires an outside justification. Either one of these facts is fine to add.
Oh, sorry, I had a syntax error. I wanted to justify things by just removing the rule R from the set of things we would be, but M is just a model, right?
Yes, M is just a model.
Yeah, so some you sort the rules in some order. I guess.
Exactly. This is exactly what we do. So we say there exists an ordering from the, we have these already variables. Yeah, variables from the variables of the program to essentially 1 to size of the variables, I guess. Such that everything that's positively here has a lower ordering than A. So for all B in BR minus, you have that the ordering from B is smaller than the ordering from A. Essentially saying, when we want to prove something, our assumptions need to be known in advance, right? You can just say we assume something that we prove later by just assuming that we prove. That's it. These two things do not give you more in terms of complexity. So we already have kind of argued about MP hardness here. MP question?
No, sorry, for all B in the minus, it should be before.
Say again, sorry.
It's only you have your for all B's that appear in the minus.
Sorry. Yeah,
Oh, okay.
totally right. Sorry. It's for all B and B plus, of course. The minus part is not essential for proving. Sorry. Exactly. So we get MP hardness already. So if we make a table, let's just say we have let's call the problem ASP because it's the ASP decision problem. You have a program and you ask, is there an answer set? So the decision problem. And let's just say for this one, we are in MP. We have shown MP hardness. Membership is easy. Just guess the set and also guess the ordering, right? So this one doesn't really give you much in hardness. It just makes it a pain for us to evaluate, kind of. And this is also the reason why solving is a bit of a pain, I must admit. So we have MP hardness here. But now there is an extension to it. And the extension is really just, we have a disjunction here. Let's just denote it with a comma. So we have many atoms here, and this is our head of the rule, and this is kind of a disjunction. So what do we mean by this? Whenever we have proven all the B's and all the B1s to BK and none of the BK plus 1 to BN, then we need to prove at least one of these A1 to AN. right? Now, the funny thing is, the definition gets a bit easier, actually. What do you mean by easier? Well, so maybe let's just, do we still need this, or can I just get rid of the ordering stuff? Yeah, okay. Because this is a bit painful. So we have our one case, set, and our justification case. Our justification case is a bit different now. We are asking for the smallest model, kind of a minimization. So for, we actually don't need this as well, but we don't need any of this anymore. Justification is just by minimality. We have a set that fulfills all the rules, but there is a smaller one. Essentially means if you use a rule, if you would maliciously use a rule and derive two things, there is probably one that has a smaller set. Except you can't find a rule because of other rules. But the idea is essentially for all set of atoms of the program. This one, if it's a strict subset of M, then M does not satisfies P with respect to M. Sorry, N. This is a specific construction for P, which we'll explain in a second. But the whole idea is we have a model of the program, and for all smaller ones, they are not a model of the program with respect to the reduct. Why do we need this? So this reduct, and this is why I don't really like this definition. It's kind of a pre-evaluation of the negation part. So what we do in this reduct definition, we get rid of this negated part. If none of these appear in M, we just get rid of the negated part. If some of these appears, the whole rule goes. So what we do is we just take the head and the body. If M intersected with the negative part is empty. Right? Yes. So we just remove this negation part. This is rather specific to ASP, and this is what makes the whole thing a bit more complicated. And it's also a bit of a pain to work with. While the first definition is quite lengthy, this one comes at the cost of an additional complication. And especially with these programs, so if you have a disjunction, it comes at the cost of a complexity increase. And they would even go farther and say, so if you allow disjunction, we are on the second level of hierarchy. Any questions about this? I will just show why in a second. But any questions about the second level of hierarchy? So this is MP to MP. So already this minimization gives us this blow up. Why? Intuitively, in general, what we need to do is we need to search for all the sets that satisfy the program, and then any subset, we need to go over any subsets in general to invalidate that the smaller one is not a model, so that we found the smallest one. So computing the smallest model, so to say, is what makes this one hard, just because of this disjunction. And now I show you a trick which is a bit scary and crazy. It's called the saturation technique nowadays. This is why we can show hardness here. It goes back to, I think, at 95 or something. Any questions so far? Or should I? Okay. So in order to show hardness for MP, we just reduce from set, right? We know set is MP hard. In order to show hardness for the second level, we just reduce from QBF. Everybody familiar with QBF? Okay. So let's just say our goal is reduce from exists a set of variables to an assignment over the x variables. So this is a set of variables such that for all assignments over the y variables, our DNF here over x and y evaluates to true. So this is a DNF here, right? For it suffices so hard. So how do we do that? How do we use the disjunction here and this weird redux construction? We really need to exploit this weird redux construction where we pre-evaluate the negation in advance. How do we do this? We have the guess from before, right? We know how to guess a variable. So for all x in x, what we do? You already had it? No? This weird loop, right? So we say x if not x prime, and at the same time x prime if not x, right? This is our guess. Fine. First level is fine from the guess perspective. Now, in order to use this weird disjunction and this default, this weird redux construction, we say for all y in y, either we set y to true or we set y to false. It's actually even simpler, right? If you think about it conceptually, this is the other rule. What we need to do now is to essentially use this concept of smallest model. How do we do that? We define we are set if we found a term that evaluates to true, right? So essentially for all the terms in DNF terms, right? In our formula, say your term is like, I want to make it example based because it's a bit of a pain otherwise to know x and y and not c. Or make this different because otherwise it would be confusing with x and y. Let's just say it's a and not b and c. When is it satisfied? What do we do here? Just add a, right? And b prime. And for c, we add c, right? Then it's satisfied. But what's with our negation part, right? We didn't use it yet. No negation except here, but we know this is easy. This is from the NP side. And this is just derived. We still need to do something. We say in the end, if we do not have set, then we don't have the solution, right? We want set. But, and here comes the weird part, is here, saturation. We pollute our assignment. We pollute our assignment over the y variables. So for space-wise, this is a bit of an issue. So for all y in y, we pollute this y if we are satisfied. So we say we get set y to true if we're satisfied. And we set y to false at the same time. So we make our assignment invalid if we're satisfied. Why is this the case? What do we need to do here? We guess an assignment, right? What we are saying is that if we have set here, then we set the variable to true and to false at the same time. So essentially saying that since you have to be set, we need to have all the y variables to true and to false at the same time, right? So in an answer set, it has to be true and to false at the same time. So in order to validate this construction, we're trying to search for a smaller assignment, right? So essentially what the only solutions to this can be, you have any configuration over the x variables and all the y variables set to true and to false at the same time. And now the goal is find me a smaller one where for this particular redux construction, one of these y variables is not set to true and to false at the same time, meaning that they are not set. So you're trying to search for something that's not set, right, in the redux. And this is why in the end, this already gives you second level hardness. And this only works because of this redux construction, because this rule is in the redux, what happens? This rule is gone, right? Because in every candidate set is in there. So this is gone in the redux. This is gone in the, depending on how you assign it. Either you get rid of this or you get rid of the whole rule. So your X assignment is kind of fixed in the reduct in this pi to the m construct. This one here. So the only thing that you're trying to do is in this co-MP check or in this answer check, trying to find a smaller Y configuration. If you can't find one, well, perfect. Then you know there is no smaller one. So you solve 2QF. Any questions about this weird construction? It's called saturation technique, and it's applied ever since for many other formalisms. And it only works with 3 ingredients. You need disjunction, you need the reduct, and you need default negation at least once. Or you need this negation at least once here. Because for these negations, you could also use disjunction, by the way. But any question about the concept? It's a bit of I guess a bit of a weird concept, but the key facts are essentially in any answer set, all the Y's are true by construction. So if you want to find a smaller one, the only chance to do so is to have not set. And then you can also have whatever sort of smaller assignment. Okay, good. So far, so good. And we can get rid of it. So what if we allow variables? So this is the ground case where we don't have first order variables. Let's just think about the non-ground case. What should we add here for our formally MP complete problem? If we have variables. And I'm even saying that our predicates are of bounded arities, so we don't have like arbitrary long predicate arities. The thing is, for ASP, this is already on the second level, and here we're already on the third level. So if we would add a line here, and we don't even use negation, then we are already on the first level, and this is the line I want to show here. So I want to show something in between here. And I will do it as follows. Let's just say we reduce from Z. So, question. How hard is ASP without negation, but first order variables? Question is somewhat clear. So we have something like, as we have seen in the initial example, there's something like R of S as a switch, right? If we reach X, then whatever, right? We reach another thing and so on. So we have these first order variables. And the proof is fairly easy, and it's also kind of eye-opening. And it's easier than the saturation technique. I mean, this will be applied later at this as well, but the proof is fairly simple. So how does this work? We have, we reduce from set. So we have something like, I'll just show it for an example. X or not Y or C, one clause. And let's just say we have a second clause, so maybe we don't need it. No, we need a second clause to show the idea. Let's just say we have C, no, not C, or it's essentially irrelevant actually for showing the idea. Let's just make it like this. What do? We cannot guess, right? We don't have negation. How should we get to our assignments without negation? What we can do is we can use our predicates. So we say, if our first clause with like variable assignment over X, variable assignment over Y, variable assignment over C. So it's really just like the same clause over X, Y, C, and over the same assignment over C and Q. Then we're satisfied, right? Does this make sense? This is something like a conjunctive query, essentially. we are saying that first order variables of our domain values, if we join, so if these have the same truth assignments, this is what we want, right? That cannot be true and false at the same time, then we're good, we're satisfied. And then what we also say, it cannot be not satisfied. But something is still missing, right? What about these C1 facts here? This is what we give as facts. So we just say, when is this clause satisfied? And we can give this as a fact very, very simply. So we just say, this clause is satisfied if, when? Well, X has to be set to true, for instance, right? So if X is true, the other ones are false, it's fine. What's another case? If Y is false, then we're also satisfied, or let's just keep with X first. So the other one would be X to true and this to 1, or let's just make it from back. So you just list all the cases where you're satisfied. And why is this an exponential? Because we only have 3 variables, right? It's 3 set. So 2 to 3 is 8, or essentially you just list all but the one case that makes it false. So it's 7 actually, right? You have all the 7 cases. And then your conjunctive theory in the databases on this fact set for all the classes individually just determines when you have set, and you say, not have set. Okay. So we get any questions about ASP and this weird formalism things with first order variables? So if we have if you allow disjunction even on the third level, so essentially it's like skipped, it's like shifted on this. So what we did here is essentially this reduction here, going from non-ground programs to ground disjunctive programs at the cost of, well, the cost is not so visible here. The complexities are kind of the same, but from the evaluation point of view, here we are in our non-ground setting, but at an easier program fragment that's supposed to be in the first level. It's just that the grounding with bounded predicate arity pushes it to the second level. But here we are at the already at the beginning without the first order variables second level, and we just do this translation here. So we ground by translating to a harder program fragment. So we ground by solving, essentially. Any questions from the remote audience? No.
Very silly question.
Okay.
When was this ASP problem introduced?
That's a very good question. The origins are from Datalog. So you might know Datalog. With Datalog, you essentially have rules without negation. So you don't have this negation part. It comes from databases, from this first order kind of setting. And then you take this syntax, you add a bit of set to it, a bit of KR expression stuff, and you end up with essentially this here.
And around what 80s, 70s?
Datalog, it's a good idea. How long is Datalog? I think Datalog is around the time, yeah, 70s, 80s. I mean, there was a long race about the semantics. What should you do with disjunction? What should be the correct semantics with disjunction? And then in 1995, this proof was shown, right? This one. That for this semantics, they call this the stable model semantics, stable sets, answer sets. You get this kind of second level flavor, or the second level complexity. But while it has traces to Datalog, it's really not that much Datalog, right? It's yeah, it's essentially Datalog plus set. So I would say nowadays it's more on the set side than on the Datalog side. And I think this proof definition is a bit more maybe natural than this minimization stuff, because it covers the basic idea of set plus everything you derive. What if, yeah, everything you derive needs to be set to true. Any other questions? So where do we go from here? Why did we do this reduction here from non-ground to ground? The problem with existing grounders is they just try all the potential combinations. So we are talking about an exponential blowup. An exponential blowup in space. And this is something you don't want, right? I mean, you encode set formulas. Would you want to have an exponentially large set formula? Probably not. So this reduction comes with the advantage of avoiding this. So we use bounded arity, and by translating to this fragment here, we essentially rip apart the body of the program. I can show some further slides, or we can also start the discussion. I mean, it depends on what we want to do. Some vote against or.
I think if you try to somehow wrap up the discussion so far in a few minutes, then maybe this would be a good time to have
Perfect.
a break within the next 7-8 minutes.
Nice. So what we have seen a basic definition of answer sets with like ordering, finding orderings that are not cyclic. So this kind of provability idea that ASP is set plus everything you derive, or everything is set to true, if you want to see it like that, needs to have a justification. The justification cannot depend on itself. So it's like this acyclic ordering based justification. There are extensions for the second level. So if we add disjunction in the head and this reduct based definition, then we reach the second level. If we allow non-ground predicates, so we have first order variables, then the complexity classes are essentially shifted by one, they increase by one, already with bounded predicate arity. ASP grounders are typically very fast. However, you shouldn't encode in such a way that you get a huge blow up. A priori, you might not see whether there is a blow up, but if there is a tool available, and we call this tool newground because it's a new kind of grounding idea. And I could also briefly show the newground approach, where we really translate the very hard rules, so very hard and long rules. So if you have like lots of a very large predicate body, then what newground does essentially, it rips apart these dependencies and makes them individual. So you have one rule with this one, and you have another rule with that one. So we avoid this exponential blow up by just plugging in all the weird combinations. We just evaluate these differently. But it comes at the cost of using disjunction. So, but we cannot avoid this cost. This is what complexity tells us. So.
Could you maybe give, I mean, since you introduced the formalism, what would be a few examples of like, how would you model some problem that we know or not, like to see sort of, ASP in action? Am I making sense?
Sure, I totally agree. Essentially, the reachability problem is not too bad. I mean, we have already seen the reachability problem, right? But you were a bit weirded out about the formalisms, right? What we could do though is we could just not use the formalism in that way. So all of these like rule-based formalizations, like reachability, but reachability alone is not hard. But if you have optimization criteria on top, or if you have extensions of maybe you want to compute like reachable paths. You want to know how many, maybe you have like a power grid or something and you want to compute specific nodes that are kind of key or that are kind of a vulnerability. You want to detect all of these like path-based, reachable-based questions. So we could at least reformulate our initial reachability problem with a different kind of toolset without this weird syntax part. So we say we reach our source, right? Whenever we reach a certain node, and this is not the definition, it's not the destination, then we guess an outgoing edge. So we say edge y. So we choose or we not choose. What do we do here for all the reached nodes that are not the target? If we have an outgoing edge, we choose it or we don't choose it, right? Now we have a lot of edges, right? This is why I had this choice, this weird syntax construction. We only want one, right? So if we reach a certain node and we have two different outgoing edges, then this is not good. And if we didn't even choose one, this is also not good. So this is why this is a bit of clone. If you write it like this, so this is why there are these shortcuts, the ones that I showed before. But you would need to specify that for all the reached ones, if there is if you reach an edge, if you reach a node and you chose one, you kind of say we have chosen for X. So there might be several combinations of or several reasons why we have chosen X. But now we say we need to have chosen X. So we need to have at least one, right? If we do not have chosen X, then this is not a solution. And if we have chosen two outgoing edges, then this is also not a solution. So what's still missing is that if we didn't choose D, this is also not a solution. Fair enough. Counting paths is hard, so the counting problem is at least a good example. Formalizing this in SAT is very annoying, the reachability part, because essentially what you need to do is you need to specify the other directions of the implication, right? Because you can't just reach something because you want it to be reached. You need to have the previous ones reached as well. This comes for free in this formalism. You get this kind of rule-based reachability. Any questions about that? You don't even need to use first order. You can just construct this in your Python program. It's just way more convenient to have this universal quantified first order variables. Because it just says no matter what you plug in for X and Y, for all X and Y, this is the rule that has to hold. So it gives you really like this universal kind of.
And what does it say? It says that you have to reach every node in the whole graph?
No, the destination. We were just wondering about reaching from source to destination.
Well, what does it mean? What does chosen X mean?
This is an auxiliary predicate.
Okay.
So if there is an X where we have something chosen, like some Y, we don't even care about the Y, right? Then X has some chosen, or X has to be decided. We could always just call it decided, right? It's really just an auxiliary predicate. And we need to have, if we have some X that's not decided, usually we also need to bound this for safety. You cannot have just negation without giving a context here. So for all reached nodes, you need to have some outgoing edge.
Okay.
This essentially is the combination here.
Mhm.
So these auxiliary predicates are quite typical in ASP. Because we cannot just say not choose, right? Because this just means you have something not chosen, but you don't want something not chosen, we want to say nothing is chosen. So this is why we really need these auxiliary predicates here, and then invert it. This is just a not reached just before. This is just a reached, and if we have chosen two, so this means like at least one, and this means like at most one, because those are different, right? This means that for all the outgoing, we need to choose them and reach the source one. I guess this intermediate thing is still missing that we had on the slide. So if we have chosen some y, then we also reach y. This one is also still missing. Right? This propagation part. Yep.
Elaborate another very basic question. What is what do you mean when you say that we don't want to say something is not chosen, but we want to
Yep.
say nothing is chosen?
That's a tricky part. How would you express that we have at least one outgoing edge? How would you express this?
Something is true.
Yes, but we need to formalize this in some sort of constraint. We can't just say something is chosen because what's the something? But yes, but we need to express in a way that is a rule in the sense of deriving something. So what you can say instead is that if you reach something and you have chosen an outgoing one, like some y, then you have decided for x. And then we invert this, this decision here. If we just ask for something not chosen, I mean, most of the things are not chosen, right? You would just query for something not chosen, but you can't, how would you write it down as an implication, what you said? It's only works directly with this negation, with this inversion.
Well, the nitpick, is it okay if the destination is not decided? Because
Yes, exactly. This is what we also have in the slides, which is here, right? Only for destination rules. Yeah, exactly. This is what we had in the slides as well. And now you see why, instead of all these rules, essentially, which ones? I think actually all of these. This is all happened in one rule here. All of the red part was one rule before. Where we just said, for all the reached vertices which are not destination, pick one. Right? We guess. We say we have to have at most two, at most one, sorry, at least one. Yeah, and that's it. So this is the at least one part. At most one, sorry, and this is the at least one part here. So you see, at least one is a bit easier to express because it's something constructive, right?
Most.
Yes, right. It's rich. At most one and at least one. The at most one is easier to express because we can just write it down in one rule. But the at least one, I mean, what's your witness in your answer set or in your assignment for the at least one? It's really, I mean, you can construct all the combinations, right? But
We're saying that at most one is easy to constructively write because there is concrete evidence showing that it's wrong. Condition. But for at least one,
you need to invert it. I mean, it's working by this negation part. Or you just list all, I mean, this is essentially what we do. We just list all the evidence and then just say, okay, not this evidence, right? I mean, this is essentially how you encode in ASP. So to have this sort of encoding, it's like atomic encoding parts, 1, 2, and then there is an even different level of encoding tricks, which is this red part, just combines everything in one rule. So instead, if you want the full confusion, then you can just write this in one rule, as we have seen on the slides, which essentially says pick one at least. Choose. Over actually it's fine like this. At least one, at most one, and then this the body like that. Yeah. So this at least one, at most one construction. This essentially says pick a subset of cardinality exactly one. So all the chosens here are cardinality exactly one. Comprises the whole red part. So
Thank you. Maybe said a little bit about it. Could you say some more? I mean, given that we have, you know, there's the Boolean satisfiability. I guess there's the integer linear programs. There's the, I don't know, max that, lots of things. But when it's like, what is a problem where like, yes, here, like, what is it that, oh, this will be so neat to write as an answer set?
How would you write this in set?
Just the right.
how would you write this in set? Like the whole reachability part. You have a problem that's built upon reachability, but it's not as easy as reachability. Like you want to count paths, you want to optimize with that. How would you write this in set? The problem is you always need to think about this other direction of the implication, right? You can't just say you reached something because you want it to be. No, the thing before needs to be reached, but all the predecessors need to be reached, right? At least one. You need to have at least one predecessor that's reached. And you need to express it for all of the cases, right? So these sort of rule-based formalizations, as apparently you have in computational biology, are the ones to go for ASP. Let's put it like that. So if you don't have like a rule, if maybe your set formalization is better, then you can still use ASP and to be honest, this is what I do a lot. I use ASP as a set solver. Why would I do that? And this is what I could briefly show at the end. Why would you use ASP as a set solver? How do you encode set? You write the program, right? Python. What do you do? C++? I don't know. I'm really curious. How do you write your set programs? PySet? I don't know.
Yeah, some program.
PySet? Right.
Whatever.
How long does it take you to make everything correct? Have an off by one error, maybe something with the variable mapping. Isn't this a pain? For me, it is. I don't know. There is always some issues. You need to test. You don't know. With ASP, you can use it as a first order extension of set. The first order extension is really not something too magical. It just gives you this first order variable. So what I often do, if you want to use set way, right? Say the set encoding. What you do is you have, okay, this color is right.
You mean writing a stat so or writing a stat encoding?
Writing a set encoding.
Oh, the problem.
Yep. So for a variable, what we can do is we guess its truth assignment, right? As we did before. So we say either it's true. This is actually sufficient. For all the variables, we guess whether it's true or not, right? And now we can just write our constraints here. If we have like A or B or not C, you just write down your constraint without having all the encoding stuff. And this is essentially just stat that's happening. There is not much ASP behind the scenes because this just tells us the ASP solver use set, just gets whether it's true or not. And this is just constraints, right? So you have like, if you do not have true of A, or if you do not have true of B, and if you have true of C, you don't have a solution. This is how I use ASP as a set solver, because I don't want to write the Python program all the time. I don't want to encode. And it is a set solver, essentially, because it doesn't use the ASP power. It doesn't need to use. This is how I write encodings in the first order style. Here, you also use usually variables. So whenever you have a variable that's, maybe you want to characterize variables, maybe you want to query some specific variables, you can just go crazy here on the first order level. say you don't allow a variable that where there is another variable where, I don't know, both are true and at the same time, maybe you have a specific naming, or you say those are in a specific subset you want to select. So you select X, you select Y, and then you give your selection variables, right? You say you have A, select B, select C. How would you do this with the set solver? You write codes, right? You write your loops, your ifs. You just write it down and say, go nuts for me, right? Or maybe just find some specific property about your encoding. It's extremely easy. You just guess and you check. And this is the usual ASP paradigm: guess and check. This is how I found a new encoding for counting recently, because I was able to try it out with immediately just running it. So
What is the encoding for counting?
I recently reduced, and I think this is pretty nice. I reduced that to like sharp 2 set minus sharp 2 set. Or we recently did this.
What is sharp to stop and sharp?
It's calling counting sharp 2 set minus the number of satisfying assignment of the other formula.
So there is two formulas and then I
You can also make it into one, but then you need a bit more than minus here, a bit more post processing. So it shows hardness for sharp 2 set already in a very basic level. You can also count here, so you need to make a counting reduction. And I played around with these encodings without hours of Python, and I like Python. Don't go quote me wrong. I'm a huge Python fan, but I don't want to write Python if I don't need to. And here's the fun part: you can even translate this into SAT. There is a translator, and it just does the same thing as you would do manually if you like, assuming you want to have it like this. So it just is a nice. If you don't use it like as a solving engine, use it as a front end for writing your encodings in a very nice first order way.
So I'm just trying to, let me try to rephrase, I'm sort of process what you said before. Let me try to rephrase and see if this was kind of what you were saying, or maybe it was something completely different. So let's go back to reachability again. And, you know, suppose I do some kind of naive stat encoding.
Yep.
Then one problem I might, so the problem is this, the sort of reachability has a kind of, some kind of inductive property.
Exactly,
right?
exactly.
And the problem is if I do a naive stat encoding, then somehow I get the problem of, yeah, but maybe the stat solver will cheat by starting a path somewhere in the middle, and from there on it looks nice. And I sort of like, how do I force it to connect everything up? And it's only justified when I'm actually starting from the source.
You can encode it. I'm not saying you
And
can.
somehow ASP almost for free gives you a way of.
Exactly.
So, but then I have a question, like suppose would ASP be like a natural formulas for writing, I don't know, some kind of dynamic programming relation?
Yep.
Or like a Hamiltonian cycle or something, where you would avoid like that you have distinct subcycles. Would you also get that kind of for free if you write it as an ASP?
The subcycles, you can write it, but
because I guess if you write, you know, if you want, suppose you want to write Hamiltonian circuit as a stat problem, then you have this problem like the naive. Your naive encodings will allow like a bunch of disjoint cycles, and which looks
exactly.
Okay, but then you have to say somehow, no, they should all be on the same cycle, and you should be able to point them out.
Exactly, this is also what you have in ILP. It's exactly the same problem you have in ILP, right?
And
you have this,
and it would go away for you if you do.
You just derive your cycle, right? I mean, it's not. You just give your cycle in an incremental way, in a inductive way, right?
Yeah, but I mean, the encoder is, suppose I have a graph and I want to write down the ASP program corresponding to that there is a Hamiltonian cycle. Would that be like a nicer
It's just a path that goes back to the original one.
Okay.
This is essentially what we wrote down.
Yeah, so it would be
It's a
cleaner than
variation.
the set encoding.
Yeah, it goes away with the pain. It goes away with the pain of having your inductive definitions, I would say, yeah.
Okay, fair enough. I guess we already talked for quite a while, but it's high time for at least a break, or maybe a discussion of whether we're having a break or whether we're wrapping up. But if we continue after the break, could you say anything, any teaser, like what would you continue with if the seminar continues? What would you do? To have the virtual audience, for instance.
We could. What's pretty interesting is that if you're interested in counting, so counting answer sets, then it's not so clear how you would count with like with these ordering based, according to these ordering based definitions. You can translate them, but at least if you're worried about the structural properties, then this is what really drives what really makes your formalization crazy. So so far it's not known whether you can express this in a way that your structure behaves nicely, which is somewhat what you need for counting. And we could talk about that.
Okay. Any questions from the audience or from the virtual audience before we take a break? So then let's hit the pause button here. Oh, what happened now?
I should need
Did
to
it say anything?
Recording in progress as well.
Yeah.
Oh, wait, what is that?
Does it automatically switch again?
No, oh, recording is not in progress. It is.
Progress.
Is that in progress?
Then that's sorry, this is a little bit confused. Then I'll just say that apparently we switched on the recording and we're back after the break. And we're going to hear more about the ASP.
And non rounding this time. Okay. Should we just
Yeah, we just go
pull this
for
over or?
That's
a bit.
yeah. Let's get it.
Perfect.
This. You just hold it. What is it? 8 seconds, and then the miracle. Yes. Fantastic. Let's go.
Perfect. So what ASP is very good at is using first order formalisms, first order flavor essentially. But this comes not for free in general. So in general, we have an exponentially larger program. So what is happening? You have your first order translation or your first order encoding, and this is then translated into the ground version. So what do we mean by that? Let's just look at the following very easy example to demonstrate what grounding does. Let's just say we want to pick edges that are not forming a triangle. A very, very simple task. So how we could specify this, we could say for every edge, either we pick the edge or we don't pick the edge. And then if we pick edges forming a triangle with different vertices, then we don't have a solution, right? Now, in general, if you do this in a very naive way, okay. So
here's a first naive question already. I'm sort of struggling a little bit with this. I mean, for a set person, it's like the rule 3 is just stupid. You're saying either if there's an edge, either the variable is false or the variable is true. Like I'd say, I already knew this. You know, you don't need to tell me. But this is because of this, you need the justification.
You need the justification. This is essentially
through the hoops somehow.
For every vertex, you need to, for everything you derive, you need to have a justification.
Okay.
And if you're not saying you pick something, then you don't get it. Okay. You need an active rule to make it.
So this is just, you learn to talk ASP, and then it's, of course, you have to do it this way.
Yes, as we did before on the blackboard. It's really just like, for everything you want to have everything you derived, you need a justification. And if you do not have this, well, then I would say the program is trivial because the empty solution is already, right? It could never match here because it requires to derive something, but we don't have a reason to derive it. Why would we derive it? So from an ASP point of view, where you need justification to set something to true or derive some information.
But wait, and what in this program forces me to actually pick? Like what, yeah, why isn't it just solution to sorry, I looked at the graph and I didn't want to pick anything.
Yes.
That's still a solution?
Yes, it's just to demonstrate the process of grounding here.
Okay.
This is really not something that we would use as is, but you would use it in combination with something else.
Okay.
So let's just say we want to pick edges not forming a triangle. You could also force to pick at least maybe 10 edges or something, right? Then we need to do something. Or you pick at least whatever number of edges. So essentially, if we have, for example, a fact, these are the possible solutions, right? Like a lot of them, we could, as you said, not pick anything. We could pick a single edge. We could pick 2 edges, or we could pick all 3 edges, right? So, and in a very naive way, if you do this extremely naively, this is kind of what the grounding, at least what we could think about the grounding, just do all the instantiations among our fact base. So the problem with this is that in general, it's exponential, right, in the domain size. As we could have very large rules, and we plug in all our combinations, so we are in this like domain size to the power n kind of criteria. So the problem is that we require exponential space in general.
For like eager grounding.
For eager grounding, but this is how it's happening. I mean, there are improvements. Grounders will not be as stupid as this one, but you can still write rules and combinations in a more elaborate way, in a more advanced way, such that the grounder constructs all the exponential many combinations. Essentially because the grounder somewhat has to, or the grounder does not really use solving techniques. It uses some shortcuts, some solving techniques, but not that many. So in general, we have this exponential sort of space requirement, and it's even much worse if we have non-ground without any restriction. We are writing next time. So this is huge, right? Non-deterministic exponential time. And the reason is why this is the case is because we can give, I'm not sure if you're familiar with like, there's a version of set where you're given in a very compact way, so exponentially smaller, and you just need to construct your set form in advance. So this is kind of how you can show hardness. You have an exponentially smaller input, and you need to construct your input, which then will be, of course, exponentially larger. So you need non-deterministic exponential time to do so. So in the unrestricted non-ground case, which is not what I talked before, there is a huge difference, right? And then on the second level, you just have a bit more. But now at this time, you might think this is, well, it's almost have a bit of MP at the top, isn't this cute, right? But there's hope. Bounded predicate arities. So if we have just say every predicate is just arity 3, so 3 first order variables per predicate or something, then we are in this table what I showed before. So for normal programs, the non-ground part is really just a mild, or mild, I mean, for you, it's maybe not mild, for me, it's somewhat mild. It goes essentially 1 level higher, the non-ground part. And what we did here is to actually solve grounding by solving. So we don't have this grounding phase, we generate grounding on our own, and we make it better by going to disjunctive programs. It's not better in all the cases, but the problem is that in general, we still, with these grounding techniques, we still have the exponential size overhead. So grounding is still not operating according to this complexity class, actually. While the problem is of this complexity, our current grounding and solvers are not operating according to it. The current grounders are still just in this potentially next time domain where they just generate, in the worst case, all potential combinations and then solve. So this picture might kind of hide information. So while this is in sigma to p, essentially we translated from this next time characterization, but not using next time power. Just our solvers work, our grounding and solving techniques work like that. So if you really want the second level thing, you can use our new ground system, the one that I was pitching before. And we also extended this to another level. I mean, why not, right? It's essentially the same conceptual idea, but requires a different reduction. Any questions about this? No. So we somehow provide an alternative grounding approach where we use complexity insights, and our approach is slightly different. So if we have rules of very high density in the body, so say you have huge bodies, and what you would need to do is you would need to find combinations of variables, right? Join the information together, like a conjunctive query, essentially, if you're familiar with that. In these scenarios, our alternative grounding thrives, essentially because the existing grounders are kind of stuck. And one of the reasons is also that in like ESP competitions, of course, you don't want to have situations where you can't even ground the program. However, you can run into these situations where you don't ground the program. And so what we did, we actually have a hybrid system going on. We use the very dense rules we do with our approach, where we rip the bodies apart. So they are solved in individual rules at the cost of using disjunction. But yeah, the advantage is that you don't get this exponential space overhead. So what we kind of do is we reduce from.
Oh, you're saying like if I have a very, very long body, I can
Yes.
split it up into 10 parts and let each part
Exactly.
derive its own sort of auxiliary variable. And okay, and then some kind of disjunction.
But how do you recover from the dependencies you kind of destroy it, right?
Yeah.
Before we had this whole thingy going on, and now we rip them apart, but we need to recover from this, right?
Yeah.
This is what the reduction does, and for this we need disjunction.
Okay.
It kind of goes over this additional level of complexity, but at least it's not exponential. So you can get some sort of semi-automatic re-encoding of problems with this. And as I already said, the system Newground does a really good job in this, and we have shown examples where instead of like grounding sizes, I think it was 30, 40 gigabytes, you just have some couple of megabytes, some couple of hundreds of megabytes, 50, 40 megabytes. So it's an order of magnitude if you translate these dense rules using our reduction. It's standalone, it can attach to any solver. It doesn't really depend on a specific solver, works with anyone. So to maybe show a one-slide summary of what we did, if you show like the grounding insights effort on the x-axis and the solving effort on the y-axis, what we did is something like this. Before we had exponential size in the instance, we reduced to something where we have disjunctions, but at the same time, this is the arity of the predicate. So we have polynomial space requirement in the domain size. Does this make sense, or any questions about that? No?
What is A here?
Arity,
Okay.
predicate arity. And this is instance size. So instead of going for the worst case, we kind of went for the worst case that actually matters, kind of. Because the existing tools, they always go for the worst case without, maybe this is not put in a nice way. So the thing is, they just do the translation of the whole program and not ripping these bodies apart. But it turns out you can rip those apart, and therefore you really just have a polynomial size explosion without the exponential size explosion. Okay, so ASP preliminaries I don't need to talk about, right? We already did this. Same kind of programs. Guess I can just skip. This is the minimality stuff. I think we can just skip the definitions. So let's just look at how we did this. Let's just look at the reduction. We call this body decoupled grounding because it kind of decouples the body elements, right? Via search, so we go via solving essentially. So let's just go to our initial example. In general, this would be like domain size to the power 3, right? You have 3 variables. There are actually better bounds from database theory, but the problem is in this setting of ASP, and this is what makes ASP different from database theory, we are talking about joins here without knowing the facts, because the facts are subject to non-determinism here, right? We don't know whether we picked an edge or not. So the effort for grounding here is still, you need to generate all these rules. I mean, for certain cases, you could think about maybe you just lazily inject them during solving time, right? I mean, you experts have said you can just inject them if needed. But if this is a way more complicated situation, it's not just constraints here, but we derive something and then we derive something else in combination. When do you really inject these rules, right? So it's not that clear how to make a general improvement. So what we did is we really just ripped those apart and solved individually. So we are assuming here a tight program without these weird positive cycles, because this makes it, we've seen these cycles, right? The cyclic dependencies. If you have these cyclic dependencies, then it requires a bit more on top. So for now, it's just way simpler to not have these cyclic dependencies. So we don't care about these orderings. We just need to find a proof where we don't order the body atoms. We just assume that everything is well behaved in the sense that if we prove something, we cannot have this unjustified cycles. So the way our reduction works is as follows. We are given a non-ground type program, and each non-ground rule, like this triangle rule, is replaced with the following. We guess what we would have in our answer set. So we just essentially do all these predicates, instantiate them, and guess them individually. So this is the guess part. We will do an example in a second. And then we ensure that all our rules are satisfied. And this is the fun part, because rule satisfiability, how would you express rule satisfiability? When is rule satisfied?
True.
We just need one of the positive bodies to be false and one of the negative bodies to be true, or the heads to be true, right? So it's ripped apart. It doesn't need the whole combination. Just because we have this guess and check thingy, we don't need to look at all of these in combination. And this is essentially what's happening here. And if we don't just have a constraint, we also need to ensure that everything we derive, everything we guessed here has foundation, right? So there's a bit, so these two kind of go along, and the satisfiability ensures. So let's just look.
What was the third point?
If we don't have just constraints, which we don't show here, or I can show it later, then we need to ensure that we have this unfoundedness here means the same as like unjustifiability. Like foundedness is like justifiability. Okay. So that we have everything we derive. It's not just guessed as in the subgraph, which we set it to true, but we don't have a justification. So the interesting point I think here to discuss is the satisfiability point. So if you look at our example here, we do this, which is a saturation encoding as you have seen before, right? So we say whether we instantiate x by 1 or by 2 or by 3. So we just instantiate these variables by 1, 2, 3, each of them individually. What you can see is that the bodies are ripped apart because we are going via this satisfiability for rule. When is this rule satisfied? If, according to our instantiation to x, y, and z, one of these has to be false, right? And this is why we can rip them apart. We are going via this additional guess overhead, via this additional guess characterization, one level higher in complexity. Does this make sense conceptually? We can also show a small example. I just want to essentially highlight why these are spread out, why these are cut apart, and that they appear negated. And then the actual encoding is a bit more involved. I mean, you see that already for this small example, it's a bit bloaty, but it goes via the saturation technique. Because if you think about it, what do we want to express here? For all instantiations of x, y, z, this rule has to be satisfied, right? How do we express for all in set? We have our exists part, right? Right? How do we express that for all something holds? Here we can express this on the second level. We just guess all potential instantiations, and then we do the saturation technique where we pollute our guess, essentially, as we have shown before on the blackboard. So I could show this trick again if you're interested in the details, but again, the conceptual part really is you guess all the assignments, and for each individual assignment, the rule has to be satisfied. Are you interested in the saturation technique? I could show this on a way easier example in more details again on the blackboard.
One thing I don't understand is that R2, it seems like you, why do you have stat R2 all over the place? Because it seems like there are so many different ways of, it seems like.
That's a saturation thingy. I will just show it on a one rule on the blackboard, on a simple rule. I think this is probably best. Can we easily switch? So
I'll just pull it up.
roughly, the idea is as follows. You guess an assignment over X, Y, and Z, and then you specify when your rule is satisfied. When is your rule satisfied? If you set X to 1, Y to 1, Y to 2, and this is false, and then essentially just list all the potential combinations when your rule is
Are they
satisfied.
exclusive? I guess that's what I don't see. Like, I don't I want.
These are exclusive by the ASP definition because you can't use these rules for deriving. You can't use them more than once. By the ASP definition, you have minimality. So these rules only justify one of these. But if you have another rule that justify the same thing, but over different rules, then you can still have the case that both of them are true at the same time. So we can still have an assignment where X is 1, 2, and 3 at the same time. Similar to before for our QBF case, for the universal case, we could set it to true and to false at the same time. This is still possible, just not by this rule. No, it's better to show an example. That's why I was hoping to show the QBF case before, but I think the QBF case deserves some more explanation actually. So why is ASP hard? We have like exists X for all Y.
Maybe unshare the screen again.
I think I did. No? It didn't go through. Essentially, we have a formula which is a DNF, right? How do we show hardness for ASP here? And let's just do a very simple.
Somehow the camera is a little bit. I don't think the camera
Yeah, I guess the camera. Is it better?
No, but we're
Should I write in the middle section or
right
maybe?
in the middle. Somehow not focusing very well. I don't know.
Is there an autofocus button or something?
It's trying to autofocus. It's just getting
It's trying,
getting
yeah.
confused by the glare. This happens with whiteboard.
Oh, okay. We can make it smaller.
The
Sure.
camera is like super intelligent.
Maybe like this. This is okay.
If you say what you write, then yeah.
So we have exists X, Y, such that for all C, we have X and C and Y, which is a very simple example, which is obviously also not true because this can be set to false, but we want to show it on a very small example. I mean, we can also make the negation here just so that we see how the negation works. So in general, for hardness, we reduce from QBF to ASP, but to show it on this small example, what would we do if we translate this to ASP? We need to guess for X and Y whether this is set to true or to false. So we have like, is X true? If not, X is false. Yeah, X is false. If not, X is true. We have the same thing for Y as well. So let's just say this is a variable. I didn't have copy paste on the blackboard. So this is a variable in X and Y. Variable, 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 variable. This is for the exists part. For the universal part, we need disjunction. So we say either Z is true or C is, or Z is false. So we have our guess. And now when is our clause satisfied? Or sorry, our DNF term satisfied? We just have one here, but to demonstrate it's fine. So if we have that X is true and Z is false and Y is true, then we're satisfied. And then there is the case where we say if we're not satisfied by Y, we don't have a solution. And in order to use this minimality criteria, we need to pollute our assignment if we're satisfied. So if we're satisfied, then Z is true, and if we are satisfied, then C is false. So we assigned Z to C to true and false at the same time. Now, why does this solve our problem? And now look again at this encoding. It's of the same style as before. Ooh, this is very. Is it better? You go to the shades, the window shades, maybe.
It's actually better.
Okay, perfect. Maybe don't need to see, no worries. Can you see?
Yeah.
No. So what we have here is really the very simplest example on the QBF encoding. We guess our variables on the extension block to be true and false, true or false. This is actually exclusive. For the universal block, we just guess whether it's true or false, and then we decide when we are satisfied exactly if this is the case, and then for the other cases we just duplicate this rule, right? Because we have our ORs here, right? So we have our DNF term, and then we do not allow to be not satisfied. But if we're satisfied, we pollute our universal assignment. So the only possibility or the only answer set to get here is where we have set to true and to false at the same time, because we say so. So what happens in the reduct? If you remember this reduct definition, well, let's just do an example about the assignment. So one specific answer set candidate would be, what would you say? Like X to true and Y to true, right? And this is actually the only one, right? X to true, sorry. Y to true, and C to true and to false at the same time. Right? This is the only answer set or the only potential answer set. But sorry, the set, we also need the set part, right? If you're precise. But this is an answer set, right? Because there is a smaller model of the reduct. How does the reduct look like? Let's construct the reduct in blue. So essentially, these rules are facts or are deleted, because for true X, what happens is like, oh, sorry. Maybe it would have been better to make a copy. So for true X, essentially, this rule, the negated part is removed in the reduct definition, because false X is not in here. So we've removed this part. And for the true, and for on this side, we remove the whole rule for X. For Y, what this means is that, again, remove this part and this whole rule. So in the reduct, we have our assignments over X and Y fixed. There is nothing to decide again. But what also happens, and this is why this all works, this rule gets removed. Why? Because we have set in here, but this only works for not set. So we remove the rule, and now it comes to the tricky part. Does there exist a smaller model of this reduct where this is removed? Yes, there is, right? So there is a smaller model of the reduct with respect to M, which is our facts as before, right? True of X, true of Y. No, we don't need Z, of course. And what's with C? we actually have freedom, right? We can just decide, for example, to set C to true, right? And that should be it, right? Yeah. So we found a counterexample. So this cannot be an answer set, but this we decided before was the only possibility to make an answer set, right? So what does this trick do? It consists of 3 components, kind of, or 3 different ones. We have our, this is kind of the exists part, right? Oh, not the sum. This is kind of the exists part. This is kind of the disjunction for all case. Default negation. We need this for making our case with the minimization. And the saturation part. Actually, it's 4 parts, but this is not blue because blue is this guy. Maybe we take another color. You can also make it like this. This is like the saturation. Let's also make this red because it kind of belongs to the same. So we have saturation, the check, the second model, and the second level model and the first level model. And the encoding, what we did for this grounding part, is essentially of this manner or of this style, where we have the universal part only works if we can set something to all the possibilities at the same time, because we need to minimize. So we could switch back to the slides, if everybody is okay with that. Or any questions about this? I mean, I guess the half hour is also done soon, but.
Go back to the slide.
But is it okay why we set the variable to true and to false at the same time? Does it make sense? We have 2 different rules, right?
Yeah.
Whenever we have set, we set it to true and to false at the same time. We can't just say that, right? This is our encoding. So the thing is, in order to make a smaller set than this one, we want to not have set, right? Because if we have set, we always get true and false at the same time. So in our reduct, in our counterexample, so to say, we want a smaller assignment where set is not contained. So when is set not contained? If we do not satisfy this term, so we just need to find counterexample where we do not satisfy this term. Well, it's easy, right? Just set C to true. This seems a bit like an F, but right? So this is really the counterexample that contradicts that this is an answer set. So if we would have an answer set, we couldn't find such a counterexample. Why? Because for all the cases of set, no matter how I put set, I always get set, assuming that this exists guess was correct. So the thing is, we cannot find a smaller one. We always get set and we pollute our assignment. So then this would have been an answer set, or what we would have guessed here would be correct would have been an answer set, but this is a negative example. Makes more sense?
So if you had the extra term there,
Yes.
X and Z and Y,
Exactly.
then you wouldn't
Or
be able
just
to
say-
hit that.
We can just say Z, right?
So yeah, sure.
Yes. So if we have this additional rule and say, if set is true, we are also set.
Mhm.
Then this gives us set, and set gives us all the assignments. So this is not a model because it invalidates this rule.
Yeah.
So then this will not exist. So maybe have another column on the true green. So if we add this, and we would add this. Then this would not exist.
Mhm.
And this would indeed be actually the only answer set, right? Because if we don't pick X or C, actually it should be false here, right? C should be false, right?
They're
Yeah.
both Both true and false.
Ah, sorry. It's the universal variable. All good. X and Y need to be true at the same time. So this is the only answer, the only solution. It's also the only QBF solution here, right? If you think about it. Except we don't have a characterization for this one, which is fine, right? I mean, it should hold for all anyway. And this is what the answer set says. For all the assignments, just at the same time, it's a bit of a weird representation, like a weird witness. But what would you expect? Maybe not the C is having nothing in it, but if you don't have anything in it, then it's all an answer set. So this is really the only way to kind of trick, or the only easy way to kind of trick ASP in having like a representation of universal variables. So the problem really is that from a representation point of view, you don't have this quantifier, right? You still have your answer sets, your sets that things that should be true. So this is a kind of a canonical representation of what's happening here. This is what makes these encodings work, and this is also how we do the body decoupled grounding in the end. Any further questions with this one? Because this is really a fundamental basic, this is this ITA Gottlob thing 95, written down a bit simpler. They use the additional auxiliary variables here and a bit of a more, bit of a longer notation, but conceptually it's the same.
Okay, so I admit that it's getting a little bit late in the day. I sort of understand half of it, but maybe not all. But you know, it's going to be even later, so I'm not sure I'm going to understand anything more. But this trick is, once I understood it fully, some other beautiful day. It's so one thing that I don't see, but I guess is true based on what you told us before, that you can pull this trick for the second level, but if I added a quantifier, then this would break. Is it because you're somehow, are you reducing from sigma P2 to answer set somehow?
Yep, from QBF.
And you couldn't do that for, like, if I had an exist for all exist, then there you could not do these kind of tricks.
Not with this formalism. You can with epistemic logic programming. There's an extension on ESP.
Yeah, but if you said this is like, if this is in sigma P2, then I guess you.
Yeah, it's easy to see why this is in sigma P2, right? You just guess an answer set candidate, and then for all smaller candidates, it should not be a set model. So you have set plus answer, right? NP to the power co-NP, which is the same as NP to the power NP, which is sigma to P. So this is really sigma to be complete. Hardness is the harder part, but easiness is fairly simple to see almost by the definition. But the trick is very neat, and maybe as a takeaway, we use this trick to ground efficiently if you have very long rules, because rule satisfiability can really be achieved by just checking all of the elements individually. You don't need this dependency that you would have in the naive rounding as written down, right, where you have this big conjunction. They just get ripped apart almost by definition of unsatisfiability of a rule. So since we go by this negative case, this is essentially what makes it work. And once you've understood this trick, you can apply this to many other nice scenarios, I would say. So, yeah. We also actually did it for the third level. I mean, if you can still add like epistemic ASP here, which is on the third level, and then we do the same kind of idea just on the third level. But it still uses this concept. Yeah. Maybe as a fun part, how this third level thing works. Conceptually, we have like this, right? And a CNF. But since this epistemic thing uses the outermost, how can we express for all exists? So it rather uses like this one. This is more what we call, not this one, which is conceptually the same, right? It's just a negation. Pulled out for all exists CNF. So. Right? So with ASP, on this level, we can only express exists for all. That's why we need to to this, we want to apply it to high levels. So we also use exists for all here. And the for all case only works with something that's kind of equivalent to the saturation technique. Why do we know this? Because if you don't have disjunction negation here, it's easy. If you don't have disjunction here, it's easy. And if you, yeah, that's it. So the conceptual syntactic ingredients to make ASP hard in the second level is disjunction and negation. And you need some sort of polluting your answer sets, or at least nobody came up with a significantly different approach. And conceptually, how would you represent your universal facts in a one set, right? All your assignments. I mean, maybe you can represent all your assignments, but then it's exponentially many, right? So if you say, if you want to have an exponential size encoding, but this is not a hardness proof, right? So as a hardness proof, this is really what has to be done without going into brute force and having an exponentially large encoding. Okay, so to wrap it up, I would just show some performance data.
How much is get the bullet for 3 seconds? You hold for 3 seconds.
Interesting. Okay. I would just briefly show performance just because I like to compare polynomial things versus exponential things. So we did this Newground thing.
Have you shared?
Yeah. Yeah, it's probably better to share it. So as already mentioned, we have this Newground thingy, which translates from non-ground normal program to disjunctive ones. And our experiments are like, I guess I would rather show this one. So we have Newground grounding size in megabytes on the x-axis, and we have Gringo ideal V grounding size if you would ground with Gringo ideal V are like two non-grounders here.
Gringo is what the class.
No, this is just the grounder. Gringo is the grounder. Class is the solo.
Yeah, but the part of the somehow I don't know what the whole tool thing is called. Like whatever.
Yeah, they call it Gringo. They call it Gringo. Gringo plus class is Gringo, but
okay.
We can also just use them independently. So we compare our grounding size versus their grounding size for specific kind of settings. And what we observed here is that if you, I mean, this is a scatter plot, right? So being here, the larger we go on the y-axis, the better for us, because this means we have a very, very small grounding size, and they explode essentially. And we stopped after 30 gigabytes. So we have instances here that are in this range where we have maybe, I don't know, a couple of 50 to 100 megabytes, and their grounding explodes, and we can still solve the instances. So we produce not only a very small compact grounding size, we can also still solve instances on this line, which is the orange part. The blue part is the performance of IDLV, and the green part is the performance of Gringo. So we see kind of this behavior that on this upper end, grounding size explodes by our competitors kind of. Here it doesn't. If we look at solving time, or at time to compute the groundings, what we see here that we have a little bit of overhead at the beginning, but so if there are instances in this area, we could just say, let Gringo and IDLV do the job, right? Let's just do a portfolio. Let's just run Gringo and IDLV maybe for 250 seconds. So we reach these solutions here. And then if they are not able to ground in this time frame, well, then we are here. So the thing is, a portfolio approach would definitely be very valuable, and was hoping for a long time to get some of these techniques incorporated into Gringo and ITLV, but I'm still working on that. The problem essentially is that it's a bit of an involved reduction, I guess, and pulling this into existing.
But isn't it do, I mean, okay, a few, wait, so the grounding time for it, there are a few bad instances where your grounding time is like truly terrible.
Yes,
And you
easier.
understand what's going on? No, I even, yeah.
Yeah, I mean, this is not too terrible. It's just, yeah, well, we get these
The
by the
quadratic
portfolio.
points are always terrible.
Yes, but we get this by the portfolio approach, right? I mean, I'm not saying, the thing is, the reduction does not come for free. It's still, it's still, I mean, I think it's a linear time reduction actually, but linear for very large programs is still very bad because we need to touch everything. So it's not that kind of nice. And to be honest, we probably also not implemented in a way that's super optimized. So this is a Python Klingo combination kind of first principle translation tool, which makes these results even more interesting actually, right? So this is really just a student-based prototype that kind of demonstrates why and how this approach could dominate, but there is not much optimization going on. So really just the first principle of essentially the reduction ideas are shown. So the portfolio approach, I'm not unhappy with that. 250 seconds, give it to them. If they don't manage, let's run new grounds. And then
what is the exact meaning of pluses also? Because you have a scatter plotter. It thinks you're scattering your grounder against both.
yes, that's why you have colors.
That's why you have colors. But then the third color is solved.
Yeah, those we can still solve. The other ones are the ones we can ground. I kind of wanted to have this insight that we can still solve many of these here. They're still orange, right?
But with which grounder, like your or
No,
the
solving
process is different from the grounding.
Yeah, yeah. It's just an overlay that shows you we can still solve the instances we ground.
Whether with your grounding, you can solve that.
Our grounding can still be solved by state-of-the-art DSP solvers. Or these just show whether with the corresponding grounding you can be solved, right? I mean, if you're here,
Pluses are always for your approach.
No, it's for both of them. Or like, what you do is I think we compared Gringo actually. You ground it with Gringo, obtain the result, and then we compare solving time of their encoding versus our encoding of the same instance.
Okay.
So this is like saying that traditional grounding doesn't only explode, it essentially is useless. And ours is like here, it can still be, it doesn't show the corresponding solving time, it just says it can solve. And our grounding time is here. So it compares grounding time, it still compares whether it can be solved. It doesn't show the corresponding solving time. The problem is there were a lot of reviewers complaining, you can ground, but can you still solve? So we overlaid this like solvability to kind of give the perception we can ground, or to show that we can ground, and at the same time, most of the interesting instances can still be solved.
So
like our grounding is not useless.
All green and blue stars can only be grounded and not be solved.
Exactly.
Like I'm trying to understand the legend. That's all.
Yeah, the remaining
I understand you're trying to pack a lot of information into your scatter plot. I'm just trying to understand the packing.
Yes.
Okay.
And with their grounding scheme, can you always solve it or no? Are these instances that can always be solved with the other grounding scheme or no?
Only the orange ones can be solved. So depending on where you see the orange ones, those cannot be solved by their grounding scheme. Right behind 1800, which is some sort of our timeout here. Whereas we can still solve them.
But there could be like the scatter plot could potentially be even more informative with 3 different colors of the pluses, because plus could mean solved by us, solved by them, solved by both. And this we can't tell, it's just a plus. Solved by some. Solved by greater equal one of the other.
I think we took the best actually. I think we actually gave them the benefit of the doubt and took the best one from them, either Gringo or IDLV compared to us. So we even took them, gave them the benefit of the doubt, because IDLV sometimes is a bit better than Gringo, right? So there are these cases like here where Gringo times out and IDLV can still solve. There are some cases. So I think we actually took the best of our competitors versus what we can solve. So essentially, I kind of think that even the solvability information is not that important, because if you just compare the task of grounding, we can still ground it. It's just that we were complaining about the selection of the instances, because it could be the case that you have instances that are useless, but you can still solve them. So our grounding is not useless. We don't produce instances that are out of hope of reach. We just need to improve our solving further to also reach the others. But the thing is, we are not increasing complexity here. The problems we solved were super hard. So, and we made instances solvable that weren't solvable before. So if you want to use this approach, you can download it from our website. I can show you the link. And you can also specify which are the rules that you want to be subject to. Usually the very dense rules, like very hard conjunctive queries, super long bodies, are the ones you would like to tackle with our approach. There are also some other plots, I guess.
Right, what was done?
This was a comparison of grounding and solving time for our solver with different categories of benchmarks. So we had path, like reachable path, we had click problems, coloring problems, and then you have the reddish ones are our performances, kind of greenish, like colors of green is Gringo and colors of blue is ideal V. So essentially all of these categories are even better than the others here. So this is like a cactus plot. We have number of instances on the x-axis, grounding is all of them on y-axis. They are sorted individual by instance. And we put all four different instance categories in one plot, just to show how it dominates actually. So if you would like to compare, you should rather compare paths versus paths. But what this plot shows is it doesn't matter. All the three here are kind of the best. So this legend is sorted from top to bottom. So I don't know. It really pays off if you have super dense rules. And it's actually not that super dense. It's really just computing clicks. I think it was like, was it 3 or 4 clicks? It's not super dense rules. It could have gone way denser. But at some point it becomes ridiculous, right? We just wanted to show there are cases, either you use our techniques or you just explode. Yes, that's a guess. So as a summary, what we did here is to kind of avoid this exponential size blowup by translating it to a fragment that's using these structures, but at the same time we have polynomial size grounding. And you can combine it with, yeah, we also did this for the third level then. I mean, it's not much of a surprise, but the interesting part is you can use our approach and you can even combine it with existing approaches. So it's some sort of hybrid scheme. Yeah, as I already said, we avoided the exponential blow up. Our framework new ground is uses actually Klingo to parse. So it's Klingo has this API where you can also do these encodings. You can play around with the grounding. So it's actually really, you even get the abstract syntax tree if you're interested in modifying, maybe rewriting. So this Klingo API actually did a great job for us in implementing and like doing these translations on this abstract syntax tree level, on the parsing level. Yeah, we're still seeking for applications in data log, except that data log usually is for, they're usually interested in data complexity, but for data log plus minus, it might be interesting. There are a lot of optimizations going on. I mean, it's really basic implementation. You can do this probably way better. We didn't do the implementation for the disjunctive programs. So far, we only support non-disjunctive programs. And what I'm really curious about is, can we improve to A? From a theoretical point of view, I think this would still be an interesting question. Do we need domain sets to the power 2A, or can we go domain sets to the power A, where A is the predicate arity? Right now, we double it. So I think this could be also an interesting question to think about. But I think you cannot avoid this doubling. And I'm not sure how to show it or if this is even the case. So from a theoretical point of view, can you go down to D to the A? I'm not sure. This would be very interesting. I'm also happy to receive some comments, but we didn't discuss the reduction in detail, so we could. The reason for this is essentially this justification point of view. because there we need not only the head instantiation, but also a corresponding body instantiation. So we have arity plus arity. It's 2 times arity in the worst case. And I'm not sure whether you can rip those apart. You always need the corresponding head instantiation with the corresponding body predicate instantiation. Or at least I think so, but I don't know how to prove it. Would be an interesting, if you are interested, I don't know. I think it's an interesting challenge. At least it's open. We couldn't solve it. Any further questions, maybe?
So if I understand correctly, the solvent paradigm is I get your ASP specification, and then I will do full grounding.
Yep.
And then I will ship to like a propositional ASP solver.
Yep, exactly.
Okay. Which I would think of as, maybe, I don't know if this is like that terminology or whatever terminology it is, I would think of this as eager.
It's super eager.
Okay. Is there any work on like being a little bit more lazy and avoid the combinatorial explosion by,
Yeah. There is.
Kind of, grounding on demand? Or...
There is. It's so-called lazy grounding. The problem is though that lazy grounding suffers from a lot of issues. While it does these like on-the-fly instantiation of rules and on-the-fly injection of rules, the problem is it has a hard time. To be honest, I think, and this is what we try to show here, you would want to have like a hybrid combination of both. Because if the grounding is super simple, or if most parts of the grounding are fine, it doesn't make sense to lazy instantiate those because you can just represent it. So I think both approaches are right. The problem is we didn't find so far the right combination. And this is also what we wanted to show here is like, you need to combine it. I'm not saying our approach is lazy, but it could be. You could inject those rules on demand. So maybe what would be interesting is some sort of hybrid approach, combining the best of both worlds. The lazy alone suffers from a lot of performance degradations. It degrades, and the reason is it sort of guesses which rules you would instantiate, and this is, I don't know. You need a nice hybrid combination. This gives at least some evidence for it.
Another question is, I mean, these are highly complex algorithms. The grounding seems pretty complicated to me, and then the solving process also. So it's a big, complicated piece of code. How can I trust that it is correct? Well, we know that the SAT community has found an answer to this.
We also have one.
Okay.
We proposed a format. We called it ASP group. It's essentially like DRED-like proof system, but for ASP.
And it works, or
yes.
Is it more proof of concept, or?
It is some sort of proof of concept, but I guess we don't have an ASP competition anymore, an active one. The last one was what, like 2014? So there is no way to force people into implementing it.
Could that proof format like conveniently support everything that the ASP solvers would do?
This is the next problem. There are lots of hybrid extensions on top. So we have this, let's call it ASP modular theory. Where
that's
So this would not be supported. And currently there was one approach to resuscitate this ASP competition in 2017, but the problem is there were not many submissions. So in the end, this whole kind of competition, let's call it area or approach, kind of died out for ASP. And these solvers, as far as I know, are not that actively maintained. They are somewhat maintained, but if you look at GitHub 3-4 years ago.
So actively maintained, so that's like Klingo or?
Klingo, I think they are going back to the developers actually. They're like their lead developer is somewhat back at Potsdam. So I think they are actually trying to improve right now. And I would not be surprised if they would be pulling KISSAT features or re-implementing KISSAT features to the ASP source. So right now there's this big kind of move to kind of resuscitate this whole solving community. But for some problems, like as already mentioned in this computational biology, if they're really rule-based, if they really have these like chains of these inductive definitions, then there is no alternative. They tried with SAT, they tried with Laurence and Morse, and I think some other experts said they failed. SAT solvers do not really work for these sort of problems. So there are problems that where ASP thrives. Also, this grounding makes it super convenient to use. And you could still go for a middle ground, which is what I do. I hate writing Python scripts for everything. So what I do is I just use ASP as a tool to generate my set clauses, which is very convenient, super fast. You have a one file thing that's given in first order and it's super easy to read. And like your Python code probably is not super easy to read out of experience, at least if you encode something useful, meaningful. But your ASP encoding is usually easy to read. And there are translators that translate from ASP to SAT. So yeah, using these sort of translation tools is still a nice way to go, and then just pulling it into GIST.
Except again, I'd like to know that these transcriptions are correct.
Yeah, but you also don't know this for SAT, whether your encoding is correct. Where is the encoding correctness? That's exactly one of the issues of SAT, actually. You know that the solving is correct, but you don't know whether the encoding is correct.
No, that's true. But now you're starting from a higher level encoding, and then I would, for SAT, I can't ask for to set the CNF is the object I'm given, right? But here you're giving me a richer object, and then it's natural to ask for more. You're going to dump it to CNF.
It certainly does not get better.
Prove it to me that you did it in a correct way.
Sure, but I mean, actually, there's work on that. Thorsten Schaub's group, they're working on, there are these first order theorem provers. So there are actually, how is this called? I forgot the name. There are actually translations from ASP to first order, because this, I think, was exactly Thorsten's argument. In SAT, the encodings could be wrong, but you can show that the solving is correct. The encoding part in SAT, the Python scripts, there are so many sources of errors. Given the first order grounding, I think there are less sources of errors, but to be honest, there are still sources of errors. So there are these encodings to first order theorem proving, and then we just use Vampire or whatever sort of first order theorem prover.
And then whatever Vampire says is the truth.
Yeah, you would need some sort of. No, but you get proof out. You get an output from Vampire. No, you don't. I think this is actually the point that you get the proof. I think you get the chain of reasoning. You get the output. Vampire applies these rules repeatedly. It finds a proof for you. So I think you get the proof. That's actually the point. That with Vampire you get your proof. It's a first order theorem prover. You get the proof. And so it doesn't only show that can you ever show that your encoding is correct? It just then shows that what you've written in first order is, but it doesn't show that the encoding is correct. The encoding level is in your brain, right? You still need to write down the encoding.
Oh,
who says that the first order encoding?
No. I mean, so okay, what you can say, like, suppose I have in the graph language, I can specify a Hamiltonian circuit, for instance, and then I write down a 0-1 ILP. Then there is, like, you could use Isabelle, for instance, to prove that the 0-1 ILP is equivalent to this graph encoding.
Sure.
These kind of things you could prove.
Yeah.
And in the same way, you could, and then you could take your 0-1 ILP, and you can write it as a CNF formula, and now you could prove that these have the same set of solutions for the appropriate notion of the same set, except for extended time. So, I mean,
with Vampire, you can at least, there is this translation tool. I just forgot the name, but I can send you a pointer if you want to.
Any other questions from the physical or virtual audience? Because otherwise, I'm thinking that we have all deserved a break at this point. And we should, did we actually ever give Markus a round of applause?
No.
We never did that even after the first time.
No worries.
Very good.
Thanks.